So the goal of this particular activity is to come up with a plausible model that can explain the inputs and the outputs of the phenomenon you're about to see. So this is a 2 liter bottle that the top is in cut off of. Here we have a beaker with some fluid in it. And what we're going to do is we're going to pour this fluid into this container and see what happens. So let's begin that process.
This is an infrared thermometer, and just getting a spot here on the container. There's some variability in the system. I'm going to spot the green one. So that's approximately the same temperature. And now we're going to pour the green one into the gray container. Just wanting to make any observations. Just record all of your observations here. This is an infrared thermometer. And
So now you write down any inputs you have and any outputs. In other words, what did you observe that was being put into the system? How much was it? What temperature was it? What did you see being output? Again, volume, speed, color, temperature, any of those types of variables. So now you have some observations, and then we can try another probe at this point. So here we're going to try another probe. We see that this is the same situation and the same green fluid right here. So now this red fluid has come out of that container and filling about 2,200 milliliters there. And let's proceed now. So now we have some additional inputs and outputs. So what was different this second time, both in terms of the inputs and the outputs? These become very important observations when trying to build our model. All right. So now what we're going to do is we're going to take the fluid that was in this container and pour it back in. So once again, you're making any observations you can about any of the inputs, any of the outputs. Um, so, again, speed, color, volume, et cetera, et cetera. So then you report down your inputs and your outputs. Now, at this point, you're going to make your model. So you're going to take the Google slideshow there and take this 2 liter bottle template here and draw what a kind of mechanism that could exist inside that container that's hidden from the duct tape, or the duct tape, that it could explain all of the phenomenon you have just observed. In other words, looking at what was input, what was output in all three of those scenarios. So your model has to explain all inputs and all outputs here. Now, once students do this, we can go on and proceed with the actual explanation. So this is a siphon situation. And so a siphon basically is a tube that starts in one reservoir and ends in either open space or another reservoir. So in this one right here, the bottle is the first reservoir here. This is going to be the input there. So we can see that that's the inlet right there. Over here is going to be the outlet. And so we can look at this from kind of Newtonian mechanics perspective. We can say that the force of gravity on one side, like let's say the right side of this siphon, it can be expressed as F is equal to mg. And so if we knew the mass in this section right here, we could total it and multiply it times g, and we would have a measure of the force there. If we look at the other side, we see that there's going to be a greater mass because the tube is going to be longer. So we'll see that F is equal to mg is going to be a little bit greater on the other side. Just again, the variable here is the amount of fluid in the tube. And so just if we were to look at this from the outside, again, if there's the force of gravity on the fluid in this side of the container can be roughly, well, it can be described as the mass of whatever is in there times the acceleration due to gravity, 9.8 meters per second squared. If we subtract the force on the other side, gravity actually pulling on the other side, then we can see that this is going to leave us a net in the downward side, which is going to pull the water in that direction. So we can see the water is going to go towards the lower spot. Now, so we have this net force, and just a simplistic explanation here of the siphon is that that net force is what's pulling it in that direction. However, there are other factors involved. Basically, the intermolecular forces need to be considered. If we're talking about water, the surface tension of water is quite significant, and its cohesion, in other words, the stickiness to the walls of the, I should say, to other molecules. So the hydrogen bonding of one water molecule to another molecule in the fluid state, and its adhesion, basically the stickiness to the container walls, in this case, the walls on the inside of the tube. And also the fact that air pressure comes into play here is that the air pressure here is going to prevent cavitation, in other words, the formation of bubbles and so forth inside the tube here. But we've known now that siphons can work in space in an environment where there is just a vacuum, so there's no air pressure. So it's actually more complex than just the simplistic model of Newtonian mechanics there that we introduced by just a balance of forces. However, that can probably suffice as an explanation because does describe certainly the major aspect of what's going on. Now, siphons will always continue till equilibrium. So if we have two cups here that are connected by a tube, we can see that this is going to proceed until the two levels are the same. So once those two levels, the water level inside and the water level, I should say the water level on the two containers are the same, then the siphon is going to finish. So we have many applications for siphons. Significant one is historically has been the use of siphons in aqueducts. So the Romans were big in terms of building aqueducts. And oftentimes they were just simply like arched structures which carried the water across like a valley. And so we can see the waters flowing here. But sometimes if you have to go down into a valley and then back up the other side, you need an inverted siphon. And that's what this is here. This actually in modern day Turkey, this particular example here. And you can see that there's the inside of the tube. Now, they oftentimes used lead in their pipes. Um, Lead has the symbol PB, which stands for plumbus, and that's where we get the term plumbing from, because plumbing was originally done with lead. Obviously, it's very toxic. They didn't know that, but we do not use plumbing anymore. This is a photograph I took at Pont du Gard in southern France. This is an ancient Roman aqueduct, so over 2,000 years old. This is my wife standing right here, so you can get some sense of magnitude. They believe that one of the reasons that this aqueduct went over the Gard River here, rather than with an inverted siphon, is that just the cost of the lead for the pipes that would be required for an inverted siphon were just too great. Most of the times that these Roman aqueducts would end in pools. This is in the town of Nimes where the Pont du Gard is actually headed. And so it was an ancient Roman town, and they brought water to it even over these river valleys and so forth, which are much lower. And they did so with the siphon. Here in Los Angeles, we use siphons to get water from the mountains up in the Sierras to us here in Southern California. If you're in the San Fernando Valley, which is this zone right here on the map, our water comes primarily from the Owens River, which is the eastern side of the Sierras. So up by Mammoth Mountain, Mono Lake, Yosemite up here, the water is tapped in at high elevation, comes down through the Owens River, and then it enters the aqueduct, and the aqueduct goes here, and it goes over various different ranges of mountains. This is actually showing the Los Angeles Aqueduct, or the Owens River Aqueduct, under construction. This is a major siphon. This over here is modern day. This is in the town of Sylmar, just where the 5 and the 210 intersect, and this is the Cascades. And you notice that the pipe is coming here as well. That is, I believe, also siphoned over that mountain, although it's not necessary at this particular juncture, because I think that the other elevation prior to this mountain was sufficiently high, and we can tell that because of the actual open cascade of water that we have right there. So we use siphons in agriculture. Like you can see this small aqueduct here, and then all of these tubes bringing water to the crops. Um, and we use siphons in home plumbing as well. And so you have a sink trap here. And when water from the sink basin fills up a little higher than this, it's going to cause the water to now flow over here, and that's going to drain the entire basin. And so that would be another example of siphons there. So many practical applications to the siphons.